Okay, good afternoon. So we will uh, just continue from lecture 2 and spend a couple more slides on the introduction, and then we will move on to the first more detailed topic, which is hydropower. All right. Now, last time, we had talked about, and I'd asked you what really is meant by renewable energy, and we were discussing, and one of you said it's abundant in nature. That's actually true. Closed loop. So, for example, I mean. Say you are using a biofuel and you are burning it, and it's releasing carbon dioxide, but then the carbon dioxide will again be mopped up by the plant, and so in a sense you have a closed loop. If you don't have a closed loop, and if you are releasing more CO2 than what you're fixing, then it is not renewable. Then it means you're over harvesting or cutting down forests. You're doing all kinds of things. So that would not be viewed as a renewable energy. Renewable energy must be that either you're completely recycling, within the loop, or it is limitless. Okay, but if that is not the case, then of course it is not renewable. Okay. And sustainable, I mean, so you can say in some ways it links up with abundant in nature, that it's an eternal source. If it really is a eternal source, then of course it would be a renewable energy. But then the issue is how eternal is eternal. Okay. So I think that we'll have to take some kind of a practical view, and maybe say that we expect that over the next 500 years or 1,000 years, that we expect that the stock will remain. Maybe it may not be eternal, but it could still be probably viewed as a renewable source. May not be renewable in some ways. Probably it would not really be renewable, but it could be a sustainable source, at least in the interim period. Okay. Another, I think we had discussed lower carbon footprint. That is important. That if you have anything which gives you a lower carbon footprint, then it has got the hallmark of a good energy source. Still may not be a renewable source, okay, but it could be a low carbon footprint source. Then we will discuss, I mean, like for example, nuclear energy or nuclear fusion particularly. Should we consider it as renewable? After all, nuclear fusion is what is taking place in the sun, and we derive all our energy from the sun. So it would not be correct to not call some parts of nuclear energy as renewable. And you may or may not like it for other reasons, radioactivity, fear of terrible accidents, etc. But in other ways, it could well be considered as a renewable energy source. Okay, now there was, or we can probably then look at a definition and say that an energy source that is sustainable for an indefinite period of time. Furthermore, the rate of use must be less than or equal to the rate of generation. If it can be, the renewable source is regenerated, at a faster rate than what you are consuming, then of course it is a sustainable source. But if it is not, then it isn't. Okay. So solar energy, of course, would be a limitless source in the sense that so long as the Earth exists, we will have solar energy, and so long as the sun exists, okay, and if the sun doesn't exist, the Earth doesn't exist, so there is no point talking about that. And likewise, because wind is produced from differential thermal energy gradients, which lead to differences in the densities of air, and that's what causes wind. And so wind also would be an indefinite source. Okay. Biomass, as I told you, it may not be indefinite. Okay, especially if you're over harvesting and cutting down forests and generating biomass, and then fuels from that. But then the forests, etc., may not get regenerated at the same rate. Okay, and so in that case, it would really not be a renewable energy source. So biomass always, you have to look at it very carefully. And all of you should first ask the question that is it renewable? Okay, and then proceed if you are convinced that it is. Okay. Hydroelectric power, yes, to the extent that after all, what is happening is that water is getting evaporated every time there is sunshine. Okay, and it's getting evaporated from the rivers, from the ocean, and that is what is forming clouds, and then that water is falling, and if it falls at a certain height, then of course we can derive hydropower from it. And so hydropower would certainly be an eternal source, okay, of renewable energy. Geothermal energy, yes, it is intermittent because especially if you are talking about things like massive heat vents or volcanic eruptions, etc., which can release large amounts of energy, but it may not be a very predictable source of energy. Okay, but obviously it is from a natural source, and to that extent, you also can't over harvest it. You can only harvest it as much as is being produced, so it would be to that extent renewable. Okay, and similarly, I mean, if you are using, let's say, tidal energy, so long as you have oceans, you'll have tides, and so you can, if you can harness that energy, then of course it is a renewable energy source. Okay. Now, as I told you, there has been a lot of discussions on whether nuclear energy should be considered as a renewable resource. I am going to cover nuclear energy because, to me, that is the most important, actually, interim solution which we might come up with. Maybe a few hundred years from now, the nuclear energy as we know it today, based on nuclear fission, may become obsolete. Many countries have already started banning it. Okay, so it's there, but whether a country like India will be able to draw enough energy from other sources. I mean, I'm talking about sources other than fossil fuel, is a big question mark, and so I think that some aspects of renewable or nuclear energy, you will have to consider it in the course of renewable energy discussions, and also nuclear fusion, which we'll talk about. That, of course, certainly is renewable energy because All you do is really take isotopes of hydrogen, and then those are basically fused, and that's how you get nuclear fusion. So that certainly is because in our oceans, etc., there is enough of these things. Certainly, there is no fear of any time in the uh, you know many millenniums that you're going to exhaust that reserve. But I must tell you that the International Renewable Energy Agency has discussed, quite extensively on this aspect, and they have declared that they will not support nuclear energy programs under Renewable Energy Agency, but that actually is for different reasons. It's not because of renewable energy, but it says that because it's a complicated process, you know, it produces waste, okay, and is relatively risky. That these are the reasons why they will not support it. But you could have a otherwise a renewable energy source. Then one would go into a discussion of whether it's a safe renewable energy source or it's an unsafe renewable energy source. But that doesn't make it a non-renewable energy source. That argument is not correct. Okay. Then we are talking about other issues. So keep this in mind. There are certain nuances and subtleties, okay, related to this definition of renewable energy. Now, we, of course, I mean, if you have to look at it, the popular ones, which we know about quite a bit. One is, of course, windmills, and there was a time when they were really proliferating. Okay, there has been a slowing down of this, and we'll show that. Solar photovoltaic, of course, is probably a booming area. Now, then these are these geysers, which can release large amounts of heat from the underground, and these are, of course, renewable energy if you can harness them. Hydropower, the dams, from which you can derive power. Biomass, sugarcane and things like that, which give renewable energy like ethanol, okay, and many other things that you can get out of it, okay. But one, which I've put in, and somehow I find that there is very little discussion of, that is draft animal power. In many countries, even today, animals do work. They till the soils. You grind different types of biomass in it and make it into usable form, powders and things like that. Or you dehusk things. Okay, there are many different things, for which you can use animal power, and some of them, of course, are extremely traditional, and so you therefore take it for granted. But there are also things which you can do with animal power, which one may not have expected, let's say until a few years back. And I'll just give you one such example from our own work. Let me see if I can find it. Yeah, this is something where all of you have heard of desalination and reverse osmosis, which is the technology that is used for desalinating waters. Is one of the biggest challenges in the world. And finding a suitable energy source is also a challenge. And this, of course, was invented and really, it's India is the pioneer, which did this work, where there are situations like natural calamities when a whole place gets completely ravished, and the power goes off. There is desperation. There's no water available, and so it was in that context that this plant was conceived, and I'll play it for you. Sorry.
दूसरी ओर खारे पानी को सस्ते में पीने लायक मीठा पानी भी बनाया जा रहा है। ये काम बिना बिजली के चलने वाली एक मशीन करेगी।
कोहलू जैसा दिखने वाला ये पूरा सिस्टम पानी साफ करने की नई तकनीक है। इस तकनीक से प्रति मिनट लगभग 3 लीटर शुद्ध पानी मिलता है। केंद्रीय नमक व समुद्री रसायन अनुसंधान संस्थान के वैज्ञानिकों ने इस मशीन का आविष्कार किया है।
पीने का जो है सो पानी है वो 500 ppm से नीचे हमको मिलता है वो पीने लायक, और जो हम इंटर करते हैं मॉड्यूल में वो हमारा 5000 ppm पानी रहता है, वो पीने लायक नहीं है। तो हम जब मेम्ब्रेन मॉड्यूल से पसार करते हैं उसको, तो वो जो है सो कन्वर्ट हो जाता है बिलो 500 ppm में।
इस तकनीक का सबसे बड़ा फायदा दूर दराज के ग्रामीण इलाकों को मिलेगा। इस सिस्टम के जरिए 3 से 500 लीटर तक पानी हर घंटे मिल सकता है। इसे बनाने वालों का दावा है कि ये पानी पूरी तरह शुद्ध होता है।
वो जो पोर्स होता है मेम्ब्रेन का, वो इतना छोटा है, तो जो बैक्टीरिया वायरस वगैरह है वो तो उससे काफी बड़ा है, तो योर वाटर विल बी कंप्लीटली जर्म फ्री। इनफैक्ट हमारे जो फीडबैक है कुछ गाँव से, देयर ऑल द वाटरबोर्न रिलेटेड जो डिजीजेस दे कुड वाइप्ड आउट।
इस पूरे सिस्टम की कीमत 2.5 लाख रुपए के आसपास है और प्रति लीटर शुद्ध पानी की लागत 3 पैसे के करीब ही बैठती है। पायलट प्रोजेक्ट के तौर पर गुजरात के कुछ इलाकों में यह काम भी कर रहा है।
भारत में ऐसे गांव की तादाद लाखों में है जहां पीने के कभी पानी मुहैया नहीं है। ऐसे गांव में इस तरह की तकनीक जो कि बैलों पर आधारित हो काफी उपयोगी साबित हो सकती है। भावनगर से स्टार न्यूज़ के लिए विजेश पाल सिंह।
Okay, so you've got an idea, the reason for showing you this also is, that do not look at renewable energy source in a very bookish manner, because then of course it seems like everything that there is to know is known and there is nothing new that you can do, okay? And what you must do is that, and especially this course, must be able to arise in you certain curiosity and enthusiasm and a spirit of trying to not only learn but to contribute, and you might be able to contribute in very creative ways. Okay, like this thing was granted a patent in the US. It has been written about extensively all over the world. Why? Because it captured the imagination of people, that nobody thought that with the help of an animal that you can generate something like, maybe 20 bar pressure, but it can be done, okay? And so, just keep this kind of thing in mind. Now, another is that, you see, what has happened is that in talking a lot about renewable energy, I think that we should not forget that the first and foremost thing that we should do is not waste any energy. Okay, that's one. I mean, it would be absurd on the one hand to be wasting energy, and on the other hand running around for renewable energy sources. Okay? That would not be right. And second, what you will find is also that there are certain energies which are treated as waste from certain applications and industries, which can be cascaded down to other applications. In other words, you may not have completely exploited the energy potential of that energy source. Okay, so that is another thing that one should look at, and this is something that I will emphasize over and over again. And later on, I will show you other examples, of energy sources. Now, can anyone tell me? Can you think of any other source of maybe renewable energy or something like that? Anything else other than what I've shown you? Does any other idea or anything come to mind?
So geothermal energy.
Huh?
Geothermal energy.
Geothermal. Well, geothermal, so of course I didn't show, but in a sense, this, these are all the, you can see steam gushing out from the, from this. So it's a kind of geothermal energy. Okay. Yes, that's one. Anything else? Now, what I want you to do is, you don't have to answer right now. That's why I put any other, but keep thinking. And I will show you at least one or two other examples of things, which we have been chucking away, okay? And it looks so innocent and benign. But then, we found that it's a great source of energy, okay? So there are, all I can tell you at this stage is there are, we will discuss it, but I want you to just think, whether you can imagine or envision other possible sources of this kind of renewable or very clean energy.
Yes, maybe using organic sources like the waste which is generated from the fields, because it leads to the generation of biogas upon
Yes.
microbial.
But that will be treated as biomass energy. Okay. Huh?
Okay.
Okay, that's part of biomass, right? Very good.
Sir, intrinsic energy from flue gas in petrolic.
Yes, so that is like the wasted energy.
Yes, sir,
okay.
from waste.
Huh? So yes, so that is what I mean by cascading down. I mean, you could have very hot streams coming out from somewhere, and for a power plant that might be the end, okay, but it could be the beginning somewhere else. You can probably even look at using it for doing thermal desalination, because so many power plants are along the coastal areas. So very good point. Okay, and yes, flue gas, but consider it as part of the so-called wasted energy. Okay, very good. Any others? Maybe I'll write down since you mentioned. Okay, I'll put one was, you said waste from fields, right? Fields, and the other one was flue gas. Okay, good. Any other student would like to make any suggestions? Okay, very good. Okay. So now what I'll do is, I have, just so that you know what is the trajectory which is being followed in India for renewable energy. Okay. You can agree with it or you can disagree with it. That's entirely an individual's perspective. Okay. But I'm just telling you what is the reality, and this is really from the government websites, this information. So this is factual information from there. Now, and what I want you to see is that from 2013, when we had this pie chart, now it is 2021. So in the last 8 years or so, there has been substantial changes. I will just call them as changes, okay? I'm not going to comment on whether it's a good change or a bad change, whether it needs some course correction, but I'm just putting up the facts before you, okay? So what you can see is that in 2013, our large fraction, okay, of energy actually was coming from wind power, okay, a very, very sizable amount, okay, and biomass, you can see biomass, okay, it was already quite small, not very big really. Solar, okay, solar was, you can see, quite small compared to wind in 2013. The small hydropowers, hydropower projects, okay, they were also contributing, but there was this is not the large dams, but the other small hydro projects, okay, and bagasse, okay, bagasse is of course like biomass energy. I don't see why it has to be kept separately. You can add up the two. If you add up the two, it's a bit better, okay, biomass energy. But wind was dominating. Now, what has happened, okay, and you can see that this is the data as on 2018. Yeah, it's not even 2021. 2018. Now, if you look at, and these figures are in megawatt, okay, you can see that we were at about 21,000 megawatt or 21 gigawatt was wind power, okay. We have increased it and we are at about 34, maybe 60%, 70% sort of an increase. Okay. Small hydropower, again, not much of an increase. 3803 means 3.8 gigawatts, which has gone to 4.5 gigawatts. Okay, not a whole lot of difference. All right. Biopower, that is this bagasse and biomass, this kind of thing. Look at it, 8041, okay, and very, very nominal increase in capacity, and it has just gone up to 9545, okay? Marginal, okay, change. This is the area that has undergone a sea change, okay. Solar power, we were at 2631, okay, we were, this is what it was, right, and this has gone up to 24 gigawatts from 2.6 gigawatts. That means a factor of 12. In other words, what you need to understand is that while if you only look at a story and a picture of solar energy and that seems to be pushed all the time, you will think that we are doing very well, okay, and we are. There's no question about it. Okay, we are. We have increased solar power dramatically, but if you are looking at any of these other ones, you will be disappointed. Okay, because there isn't simply that kind of impact, which you can see, right? So today, if you were to look at this pie chart, this would be like, well, wind would be still the largest, but it would have undergone a dramatic change. So probably wind would be this part, over here, and this part and this part, if you combine, that would be solar. So huge change which has taken place. Keep that in mind. You need to always ask, okay, that why has this happened? Why has this happened? that we have focused so much more on solar as compared to anything else. Maybe we were following the wrong policies before and we have corrected policy. That's possible. Okay. Or it could be some other reason. I don't know. I mean, if we are looking at it again 10 years from now, whether the situation will again continue to go the way of solar, or there will be again another U-turn, which takes place, only time will tell. It is possible that wherever there was an opportunity to put up windmills, wind power, we have already done it. And now there isn't that many of good locations left. So, maybe that's the reason why we have saturated. Okay? Same is the case maybe for hydropower. We are not able to really find good new opportunities. Okay, and maybe the same case with biopower, because after all, where is this additional biomass going to come from? And especially, if there is more and more deforestation, there is less of biomass available. So where is it going to come from? So these are the kinds of issues that you need to grapple with. Okay. Now, what I will do is that there's a third assignment which I will ask you to do, and then once you submit it, I will grade all the three together. Okay, the ones that you have already submitted plus this. Now, what you see is that when we are talking over here, anytime there is this talk about renewable energy, invariably it is about power, and you can see renewable energy by installed capacity. This capacity is power, electrical power. Okay, all the stuff that we are talking about is electrical power. Okay, and now the question is that, look, I mean, renewable energy is more than generating electricity. There are so many applications of renewable energy, right? Like, for example, and which we take for granted, but and yet it's so important. For example, how do we dry clothes in India? All of us basically leave the clothes to hang, right, outside, and they dry. Do all of you do that, or you do something else? And your parents? Huh?
Yes, sir. Yes, sir. Dry.
Yeah, so everybody does that. Now, but don't think that everybody in the world does that. You go to the US, I mean, there are all these, just like you have a washing machine, next to it is a dryer. They put their wet clothes from the washing machine into the dryer, and they use electrical energy to dry their clothes. Of course, it dries in half an hour and they're fine. But who has accounted for that renewable energy? That how much energy we actually saved, in drying out clothes on the outside, and letting it dry. And it's not just solar, but it's a combination, because it's the more breezy it is at the time that you're drying your clothes, the clothes will dry faster. It's really a combination of solar energy and wind energy, which does this. And today is what? Today is September 9. So by the way, this is India's population as of yesterday. We have reached almost 1.4 billion people population. Okay. Now, what I want you to do is that I want you to compute, what is the saving in energy that we realize from drying our clothes naturally. Okay, the way we do it in India, and as I told you, many parts of the world they don't. Okay, Europe, America, etc. They dry it using artificial forms of energy. Okay, now you may have to make certain assumptions, and like obviously per person on average, how many kgs of clothes are washed in a day, or how many grams, what is the moisture content that remains in the cloth at the time that you hang it to dry. Okay, you of course know about latent heat of evaporation, that etc. So why don't you work out, and you work out what is the saving in energy per year, that we realize basically by drying out clothes outside. Okay, now that is not necessarily the only one. There are many other things that we do where we are using renewable energy. It is just that somehow, if you didn't apply your mind, okay, and you see these things, you would think that that is the only application of renewable energy. What nonsense! That's only a power. That's only one part of it. Okay. But what happens is, many times our decision making or planning actually is, they don't really look at things in a much more comprehensive way, which they ought to. Okay. So I want you to think of and list out other such unaccounted uses of maybe solar and wind energy. And for that matter, even biomass. You see, the biomass that we have talked about is the biomass that is used for power generation. But I mean, in villages, etc., I mean, people collect wood and twigs and all kinds of things, and they cook their food, etc., with that. No? So just try to see it's thermal energy. It's not power. Okay, but nonetheless, it is serving a purpose. Okay, so I want you to really look at this, and try to make a good list. Okay, and I don't want you to just rattle off it is used for this. You have to apply your mind. Okay, maybe look and search for statistics and see if you can quantify, right? And it's always so exciting when you see the larger picture. Okay? When you see the larger picture that this translates to so many gigawatts of energy or this, that, then it looks interesting. Okay, so that is your assignment 3. Oh, I had said no need to submit, but I think I'll change my mind. I will say submit next week. Okay, and then I'll grade all together. Okay. All right. Any questions around the assignment? Is it clear to everybody? All right. Now what we'll do is, we are through with our the introductory portion of this course. Okay, and now we will be going into specifics. Okay, each of these renewable energy topics, and we'll try and deal with it in some amount of detail. Okay, it is not the kind of detail which will make you a international expert. Okay, but you will certainly come back, or definitely what should happen is that you should become more knowledgeable about the subject. Okay, and that will be true about everything. Okay, you must become more knowledgeable after this course. All right, and so that's really the objective of the course, and so that you can also think rationally yourself and think in a quantitative way. All right, so let us look at what really is hydropower. Okay. What is hydropower? You are really evaporating water from the land, or means rivers, from the ocean. Obviously more from the ocean, because the ocean is the larger part of the world. Okay, and where are you evaporating it to? You are going all the way up to the clouds, big height, right? To which you have taken the water, okay, from here. And then what is happening? It's raining, okay, and then when it rains, okay, it can rain. The rain can fall back into the ocean, okay, and ocean, as you know, is the lowest point on Earth, right? So that's why we say sea level, and so you are not really going to be able to extract any energy from the water that falls on the ocean, or even if it falls on land, but that is land which is more or less close to the sea level. Okay, but you see, I mean, rains can happen in the mountains, right? As it happens in our Himalayas, and you form glaciers. Okay, there's so much of snow which is produced, or need not be necessarily always in the mountains, but it could be at an elevated point of land. Okay, and there are many such places which are at a height. Okay, so anytime something is at a height, what kind of energy does it have?
Potential energy.
Right, potential energy. Okay, so and you could do that simply because the water went up to the clouds. It is a much higher level, and imagine if we could have had all parts of the country, if we had places where you could store water in the hills. Okay, then because after all we have got hills, and we don't do anything with the hills. But if we could convert these hilltops into, say, large reservoirs, and so that they become catchment areas and water falls from there, one is that I might be able to derive hydropower from it, and also it would make the cost of distributing water that much less, because the water would be distributed by gravity. Whereas, if it is in Powai Lake or one of these other lakes, again the water has to be pumped, right? And if you are living in a high-rise building, it has to be pumped all the way up. Okay? But if you were to take water from the hilltops, then automatically you would save quite a bit of energy in distributing. Okay, and plus you might be able to derive hydropower. So and maybe some of you should go and look at, are there such opportunities that we have, like in Maharashtra or in some of the other states which are not being utilized? If it is not being utilized, think about it. Okay, that can you do something clever like that? What would be involved in doing it? Okay, so it's all about the hydropower, really about exploiting the potential energy of water that accumulates at a height when it comes down as rain, and the flow of that water, which converts the potential energy into kinetic energy. Okay, and that's really the energy that we extract, in deriving power. Okay, so let's read this. Hydropower energy is ultimately derived from the sun. Okay, because it's the sun which is evaporating the water, which drives the water cycle. In the water cycle, rivers are charged in a continuous cycle, and you know that many of our rivers actually start on in the hills. Okay, and so they are at a height, and so it is really coming down through a considerable height before it gets discharged into the sea. Because of the force of gravity, water flows from high points to low points. There is kinetic energy embodied in the flow of water. Okay? So that's really the sum and substance of hydropower. Okay. Now let us look at. Let me ask you, how old do you think hydropower is? For how long has it been around? Hydropower means actually generating electricity.
100 years, sir.
100 years. Any others who would like to say? So you think it was around 1920 or thereabouts, right? Okay. You know, the first hydroelectric power plant was constructed in 1882. So you're not really very badly off. This is about what? About roughly 140 years ago. Okay. And it was constructed in Wisconsin, the state of Wisconsin in the US. And what was the motivation for that? Because by that time, Edison had already, popularized the light bulb, and, it was such a great invention because the fact that you could light up cities, okay, it was one of the most spectacular things, which happened. So obviously they needed sources of electricity. Okay? You had a bulb, but you need electricity, right? So that's what this really was. What was constructed, and later on it was called as the Appleton Edison Light Company. It's so obviously there was a great application which had been created, and that is what gave birth to the to this hydropower. And it's interesting. You will be surprised how much in tune with the rest of the world we were many years back. Okay, so 1882 was the first hydroelectric power plant in the world, and in India in 1897. So within 15 years, we had our first project. It was in Darjeeling. Okay, and by the way, this is also the first generation of electricity in our country. Okay, and that's 1897, right? So just over 120 years ago. And today, when you think about the world, electricity, light, everything, it definitely seems like it has existed from eternity. The world wasn't like that. The world was a very different place. Okay, so it's also possible that maybe 100 years from now, if we cannot generate very good sources of energy, maybe the world will go back to that. We may not die. Civilization may not be wiped out. Okay, we may go back 200 years. That's what might happen. Okay, or because there'll be a lot of fight for the last bits of resources, a lot of people might get killed in that process. But it may well be, the scenario need not be that either you have these so many gigawatts of power, etc., or even you'll just say there's no car, there's no AC, but that is the way it was 300 years back. There was no AC, there was no car, there was nothing, there was no electricity. Okay? So we might go back to that kind of state, okay, if we are unable to find sources of energy. Okay. Okay, so what exactly happens now? Originally, when people discovered the potential of the water at a height, they were really not doing it for generating electricity. Okay, but so you had these kinds of water wheels. You can see how the water is falling and the wheel is turning, and gears were very well known. Okay, so you could run a gear, so you could convert something from a low speed high torque to something like a high speed low torque, and you could run certain operations. Like for example, the one that I showed you with animal power. I mean, one could equivalently have done something like this with this. Okay. In other words, you can convert potential energy into mechanical energy and use that mechanical energy. All right. So, for example, they were using these water wheels, to grind grains. Okay. So all these grains used to be crushed with water wheel. Okay. And sawmills used to be run with water wheels. So these are not based on electricity because it would be so stupid, to convert mechanical energy into electrical energy, and again electrical energy into mechanical energy. If you can do a mechanical to mechanical application, well, that would be nice, and so that's what these things are. Now, then came the birth of what are known as turbines, the water turbines, and these are the ones which were used to generate power. Okay, water turbine is not very different from a water wheel. Okay? But what happens is that it's an enclosed structure, and the way that these things are constructed, the percentage of the pent-up energy in the water, the potential energy which got converted into kinetic energy, and which you're harvesting, that percentage started improving. Okay, because here actually what happens is that when the water falls, a lot of the water energy is still available. It's not really all getting introduced into the water wheel. Okay, and that is what basically one is improving with the help of turbines. Okay, now so then what happens? Well, so this is your dam or lake from which from a height water is coming. Okay, and from a height potential energy is getting converted into kinetic energy. Kinetic energy is what is driving this turbine. Okay, and on the other side you have a magnet which is connected to the other side of the shaft. Okay, and so as the turbine is rotating, the shaft is also rotating, and the magnet is really surrounded by a electric coil, and you know that that is Faraday's law of induction, that if you have a moving magnet, in an electric field, okay, that you'll actually generate, in a coil, you will actually generate an electric field, and that is really what we call as electrical energy, which has an electric potential. Okay, so that's really your generator, and then that electricity is what is fed to the grid. Okay, and from which we draw power. Of course, this is the case for hydropower, but much the same principle is applied across the board, whether it is wind energy, whether it is nuclear energy. The basic operational principles by which you generate power is the same. The only case where you have something which is dramatically different is solar photovoltaics. Solar photovoltaics generate electricity without requiring any turbine. What a mind-boggling invention it was. Okay? But all these other ones really are based on the running of a turbine, and the turbine then running or rotating a magnetic field, and the magnetic field inducing a current. Okay, And that's really what the whole thing is all about. So let us now quantify, right, how much electricity can be generated by a hydroelectric power plant. Okay, so you can see a typical dam, the water falling. Okay, and the two important things which you need to know, right? One is that what is the flow rate of the water? I mean, how much water is falling per second? Okay, because and where is it falling? It is going and hitting the turbine, right? That's really what is happening, and so we need to know what is the flow rate, the quantity of water flowing at a given time. All right, and the second is that we need to know what is the height uh, over which this water is falling. All right. So if it is a higher height, will you get more energy or less? If the water is falling from a higher height,
More energy.
More energy.
yeah, you'll get more. And why? Because potential energy is mgh. Okay, mass into acceleration due to gravity multiplied by the height, right? That is your, so the water over here at this point has only potential energy, right? And once it is falling, okay, the potential energy is getting converted into kinetic energy. And there is a velocity of the water, and that is what is then being utilized in turning the turbine, right? So these are the two important things that you need to know, right? Now, the equation which is derived, for calculating hydropower is I've given over here. Power is in kilowatt, right? And that is equal to the head multiplied by the flow multiplied by the efficiency. What is the efficiency? Efficiency is the water which is falling on the turbine, all the energy of that water is not extracted by the turbine. Okay, and so only a part of that energy is actually utilized, right? So that is the efficiency. So if all of it was utilized, the efficiency would be 1. If a part of it is utilized, it would be a fraction. Okay, and divided by 11.8, this 11.8 term comes only when, and in earlier days, people would express the head in feet and the flow in cubic feet per second. Okay, that was the standard nomenclature which was used. Okay, but if I express the head in meters and the flow in cubic meter per second, then there would be no 11.8 term. So let us try and see. Firstly, you can imagine that there is a huge amount of work that has gone on over the years in trying to improve the efficiency. Because if you get only 50% out, then I mean you have wasted 50% of the potential energy. Okay, but if you can, on the other hand, get 100% out, wonderful. Okay. And so earlier, in the dams, they had reached a figure of around 0.6, as the efficiency. And today, in the best of plants, with improvement in design, they have been able to raise that to 0.9. Okay, so that's a huge improvement. Okay, which has taken place in the efficiency. So keep that in mind. And the standard figure today is roughly about 90%, or 0.9. Okay, so now what we know is that what is really going and hitting the turbine? It is really the flowing water, which means it is the kinetic energy, right? Now, when we are talking about power, we are really talking about energy per second. So I can express this as kinetic energy per second. And where is this kinetic energy coming from? From the potential energy. Potential energy is getting converted into kinetic energy. Okay. And what is that? The amount of water that was falling from that height. Okay. And then you have got basically the height from which it is falling. Okay. So that is potential energy mgh, mass, into acceleration due to gravity multiplied by height upon second time. Okay. So now I can also express this if I take the mass upon second, as one term. Okay. And then I multiply it by g and h. Okay. Then I'll end up with the same thing. This is the same thing. Instead of writing this, I can write kg per second multiplied by g multiplied by h. All right. And so now let us take a case where the amount of water which is flowing, the rate of flow is equal to y cubic feet per second. Okay. Why? Because this is the convention which people had used. Okay. And let the height be z feet. Okay, that is falling from a height of z. Okay, and let the efficiency be eta. Then what would be my hydropower? That is the same thing as power, this power. Now that would be equal to this figure. Okay, now this is the water power at the turbine inlet. All right, water power multiplied by eta will give me the hydropower. Okay, which means the electricity generation. Okay, if I only look at the water power, that is how much energy was there in the water, that will be just simply the potential energy per second, which is equal to the kinetic energy per second. All right. So and if I multiply that by eta, then I'll end up getting the hydropower. Now the water power was, or the water flow is expressed in cubic feet. So it's volume. Okay, this is a volume term, volume per second. Okay. So what do I have to do? What do I have to know to convert it into mass? To convert volume into mass? What do I need to know?
Density.
Wonderful. Okay. What is the density of water?
1000 kg per meter cube.
Right. So that is your 1000 kg per meter cube term. Okay. Multiplied by y feet cube per second, y cubic feet per second. Right. That is what is given over here, y. Right. And now what I do is that because the unit is in watt, so I need to have everything expressed in meter, kilogram, second. Right. So I need to convert feet into meter, right? So the conversion is 0.3048 meter per feet. Okay, so I'll take into 0.3048 meter per feet whole cube. Okay, that's what I'll if I do, then I'll basically convert it. So now what will happen? This meter cube, meter to the power -3 will cancel out with this meter cube, because one is in the numerator, one is in the denominator. Okay, this feet cube will cancel out with this feet cube, right? And I'll end up with 1000 kg into y per second. Right? That's what I'll have, right? So that is my flow rate in terms of mass flow rate. Okay, not volume flow rate. Okay, so I've got my mass flow rate term here, that is the kg per second term, multiplied by acceleration due to gravity. Okay, and what is that? It is 9.8 meter per second squared. Okay, And then the height, again, I'll convert feet into meter, which means Z feet into 0.3048 meter per feet. So feet and feet will cancel out, and this will become meter, right? So what did I end up having now? I have got a meter term here, I've got a meter term here, that becomes meter squared, and then I've got a second to the power minus 2 term here, and I've got a second to the power minus 1 term here, so that is second to the power minus 3, okay, and I've multiplied by eta, right? And so I can now express this as 1000 multiplied by, and if I take 0.3048 to the power 4, okay, it's cube over here and 1 over here. Can somebody tell me quickly what is 0.3048 to the power 4?
0.00863.
The unit will be kg meter squared per second to the power minus 2, and then that other second to the power minus 1. If I put it, this is the unit of, what is this unit? Joule, right? Kg meter squared per second squared.
Yes.
Okay. So it becomes joule per second. All right. So I can write this as joule per second, which is equal to watt. Right. So I've got 1000 term here. Right. 1000 because I have to express it in kilowatt. So this 1000, instead of writing it as watt, I can subsume it in kilowatt. Okay. So because I've got 1 kilowatt is equal to 1000. Okay. Just do that. 0.00846 into 9.8. How much is that?
0.0845.
That's, I'm sorry. I'm 0.0845.
846.
Okay, 846, I think.
846.
Yeah, what I'd written. Okay. And take the inverse of that.
11.82.
Correct. Now you know where that 11.8 term comes, right?
Yes.
So what do I now have? I have, what have I taken? So it will become now x, y, z, eta upon 11.8, where electric power is in kilowatt. Okay. So I might, give you things like this to just calculate or derive. Okay. You should be able to do it. It's quite simple. Okay. Nothing that you don't know. Okay. So let us go through one calculation. All right. So this is a dam, a famous dam, the Roosevelt Dam, right? And the dam has a height of 357 feet, okay? And the head, okay? The actual head means, the dam has a height of 357 feet, but the water does not necessarily fall from the top of the dam. There is a hole which is created somewhere below, okay? And so the net effective height is 235 feet, at the time that it is hitting the turbine, okay? 235 feet. And the flow rate is 2200 cubic feet per second, right? So I'll just use that formula. Power in kilowatt is equal to head into flow into efficiency, and efficiency was 80%, which means 0.8. Okay, and divided by 11.8, so 235 is the figure, multiplied by 2200 cubic feet per second, multiplied by 0.80, which is the efficiency, divided by 11.8. Okay, and just work out this figure. Do you get this answer? 35051. Just see.
So 35,051.
Yes, sir, it is right.
You're right. It's right, right? Okay. So the rated capacity, of this dam, the Roosevelt Dam, is 36,000 kilowatt. All right. So, if you are not getting like something is very seriously wrong and you find that you're getting a much lower value, the dam is not working properly. Maybe the turbines there's a problem, or maybe there is siltation. There are all kinds of problems which have taken place. Okay, so there could be many different reasons why it could deviate from whatever is the rated capacity. But I hope you understand how to calculate rated capacity. Okay, now these systems, which we talked about, are what is known as an impoundment system. Okay, civil engineers will know this, of course, very well. All right, what do you actually have when you are making a dam? You are effectively, instead of letting the water keep flowing, and flowing all the way to the sea, you are just building a wall. Okay, it is like a highway, where traffic is flowing and suddenly they encounter as if a wall on the highway. Okay, that's what, and you stop. Now what will happen to that water which is flowing? It will keep flowing. Okay, and you will need to, because if it's raining well, okay, the water will keep flowing, and if you can raise the height of the wall, obviously you can create a larger and larger capacity of how much water is being stored, okay, in the reservoir. Okay, and so that's the importance of this, the height of the wall. But what it also means is that the more water I store and I raise the height, what am I going to do? All my adjoining areas, which were at one time, they were perfectly habitable areas, they will all get submerged. Okay, and so you would have heard that there are lots of fights, court cases about increasing the height of a dam. That is because more I increase the height, more people will get displaced. Okay, and so it affects people, right? So there is some benefit and there is some loss. There are many people who are also very badly affected by the construction of these large dams. Now, so that is what you're doing. This is known as the process of impoundment. Okay, where you are now, by creating a wall, you are preventing the water from flowing, and it will just build up. Okay. Now, what you do is, you can see it is not right on top of the height of the wall, but somewhere below, okay, there is this hole that has been made, and from here the water will fall. Okay, so that's why, in that previous one you saw that height is 357, but the distance over which the water falls is 235 feet. Partly it is because it is falling from a lower height, not from the top. Okay, and the second is because the turbine, etc., where it is placed, these are also giant turbines. They will occupy a height. So when the water comes in, you can see that it is not necessarily at the ground level. Okay, it will be slightly up. Okay? So it is this net height which I have to consider, my 235 feet or whatever. Okay, so that's what is happening. Okay, that is the entire process, and once the water is going through the turbine, the water is again flowing on this side, and then of course the water is being taken to agricultural fields. It is being distributed in different parts of the state, or wherever this dam is, and it can travel large distances, and basically be used for subsequent purposes. So the height was required really mainly to derive the power. Otherwise, I did not need this dam. Okay, and partly the dam also serves another purpose, that you see, when, like, suppose I've got excess rain, I've got a lot of rain, and then there are some times when there's drought. Okay, now if I have a very large reservoir, then during good times, when there's a lot of rain, I can fill up more and more water. And so even when there are situations when the rainfall is less, I may still have water available in my reservoir to be able to run my hydropower system. Okay. So obviously a large capacity has advantages, but then as I told you, the disadvantage is that there is massive flooding, over very large areas of land, and so a lot of people get displaced. Okay, let us look at now some of the very large dams. The largest dam in the world is in China today, and it has got a height of 305 meters. Unbelievable. I mean, you can see we've got one of us quite a big height, 260 meters. The Terry Dam, all right, but this is in excess of that, okay, and of course the length in that dam is much larger, so the amount of water that it holds, it's massive, and so these are our large dams. The Terry Dam, in Uttarakhand, you can see the height and you can see the length, and you can calculate the reservoir capacity, and you can work out, from the cubic meter of flow, whatever is known for this, and the height, I can work out. In this particular case, the installed capacity is about 1000 megawatt. Then we have got the Bhakra Nangal Dam again in Punjab and Himachal Pradesh, and that generates about 1325 megawatt, and you can see comparable lengths, okay, and comparable height, though this has got slightly larger height, but then the length of this dam is larger than this, and there's a difference, I mean, again, there are differences in some of these other factors, what is the actual height over which the water falls, etc. And between these two dams, you can see a large difference in the capacities of these two dams, this one and this one. Okay. Then you have in Odisha the Hirakud Dam with a much lower height, but a good capacity, and the length is 25.8 kilometers, of this dam. Okay. And but overall, I think the height through which the water falls is less. Okay. The Nagarjuna Dam in Andhra Pradesh, okay, 816 megawatt, and the one today which is the largest is the Sardar Sarovar Dam in Gujarat, and this is the one where there was a massive controversy because of when I think they raised the height still further than 163 meters, and it's got a very large capacity, and it's got a generation of something like 1450 megawatt, and it serves not just Gujarat. There are 3 states which are drawing the power, from the Sardar Sarovar Dam. Now, dams are also very costly to build. Okay, there's a huge expenditure in building a dam. The second thing is that there are safety issues. Like once you make the dam taller and taller, imagine if suddenly the wall were to collapse. Something happens and the wall collapses. Can you imagine the calamity of this amount of water suddenly flowing out? Okay, it can create havoc, right? So these are the basic issues, with large dams. They've got advantages, but they've also got disadvantages. And let us look at some of the environmental considerations that you need to keep in mind, while looking at these dams. Like this place, Glen Canyon. I mean, it's a beautiful place. There was a lot of recreation, boating, this, that. When they converted into a dam, all that is gone. Okay, and it has lost completely its recreation value. Okay, uh, there are very serious problems that you can have flooding. As I said, there can be massive flooding. Okay, because of these height. Now, what happens is that you see a river is a flowing water, so the water is continuously getting aerated. Okay? But whereas when I construct a dam, the bottom parts are, over a period of time, there's no aeration of the water. So the quality of the water actually becomes very poor in some of these dams, and the fishes cannot survive sometimes. Okay, and then again you have got a problem that there are many dams, where uh, there are so many fishes, which travel upstream. Okay, you cannot. How will the fish travel up? Okay, and so they make, there are special constructions of steps. There are staircase-like things, and the fishes can gradually, climb up and go on the other side. Okay, but these are very, very serious issues. Okay, flooding, fish population, water quality. Okay, and because you have a dam with so much of water, okay, over there, that many of these dams have had problems of earthquakes, seismic activity. Okay, so there is always that risk, that you could actually induce an earthquake because of the construction of very large dams. So these are all the things that you need to keep in mind. Okay, and they're all very important issues. Now, as I told you, there is a massive adverse effect on local ecosystem. One is, of course, that people get displaced. Their places are all flooded. Okay. Then what happens is that it is not only people getting displaced. Suppose, like, let's say I do flooding, and there was, let's say, a lot of greenery, lot of trees, etc. What will happen to those? They will all die. They cannot survive in such waterlogged places, So many times what happens is that these dams, all this vegetation which was there, which will slowly die, and after it dies, what will it do? It will release large amounts of greenhouse gases, methane, due to rotting. Okay, so a dam we think of as very clean energy, but a dam can also produce large amounts of greenhouse gases. Okay, because it takes a long time, for all of the effects to be felt. It's not as if it happens in half a day. That effect can last for years. Okay, so there's a very serious problem. And as I told you, because the water gets stagnant. Okay, so there is a massive depletion of oxygen, okay? And that can affect the fish population. Okay? So, and not just fish population, it could be other kinds of things that require oxygen. So keep this in mind. Okay, that there are some things good, some things bad about these large dams. Okay? Now, there are also things which are known as low head, low impact hydropower. In other words, you see, a river is what is flowing from a height and is going down, okay, all the way to the sea level. So you can also, you need not necessarily have these large walls, you can actually make things which are of a low head. They won't give you lots of power, and what you do is that you can divert a part of the flow, from the river, and generate power, from that, okay, and then later on, that water again merges with the rest of the river, and off it goes, and so these are basically known as run of the river systems, okay, and they basically just make use of the natural flow. Okay? There is you don't really construct big walls. There are these are known as weirs, and below this, basically the water, you can artificially create a certain height, even in a flowing river, through things like the weir. Okay, you don't have to go into all the details. Just need to know that there are ways of constructing and making sort of artificial heights in a river, but these are typically quite low head, and but it's okay, you can generate power for maybe adjoining villages, etc., which are in the area, and maybe a few thousand people, 10,000 people might get their power from this kind of low impact, low head hydropower projects. Okay, then there are also micro hydropowers. One is, of course, I showed you, but you could also have, as I told you, waterfalls. There's so many waterfalls, right? We see them all the time. You can actually generate hydropower projects, for those waterfalls, right? Natural waterfalls, and they are typically not very large capacity. They are not megawatts and 1,000 megawatt and all, but maybe in the sub megawatt range, maybe 100 kilowatt to 1,000 kilowatt, that kind of range. Okay, and those are the kinds of things, and you might be able to construct many of them, okay, without any very serious environmental consequences. Okay, so keep this in mind, and I think probably there is an opportunity to survey different places and see where there is an opportunity for such micro hydropower plants. That would be a wonderful way of generating renewable energy. Okay. As I told you, a low hydropower, low impact. When we say it's a hydropower project with a low impact, okay, what does it mean? One is that you are letting the river still flow. You're not stopping the river flow. You are maintaining water quality. Okay, you are maintaining watershed protection. Things are not getting flooded. Okay, you are allowing the passage of fish and protecting them. Okay, you are not threatening endangered species. Okay, you have a recreation. Whatever recreation activities, etc., one had, those can continue in most of these places. Okay, and so these would be typically what we would call as low impact hydropower projects. Okay, now let me also tell you that there is a opportunity to think imaginatively, and especially I keep saying this in for Maharashtra, but many other places. When they held the previous Olympics in Rio de Janeiro, okay, in Brazil, what they did was something very interesting. Okay, there are places in Brazil, in Rio, I've been to those places, very beautiful, where there are tall hills, okay, and below that are rivers, okay, and so what they were doing was that they were using solar pumps, to pump up water from the river to the hill, okay, during the daytime, when there is solar energy, and they created reservoirs on top of the hill, where the water was being pumped, okay, and then at night, they were letting this water flow, okay, so it became like hydropower, and they were generating electricity, okay. So during the day, you use the surplus power, and anytime there is surplus power, lift water, lift water to the height, okay, and and after that let them fall. Okay, and so when we have got so many hills, I think that especially also if you've got hills not too far from a sea coast, maybe within say 50 kilometers, okay, you can actually pump the seawater to a height, or during the monsoon time, you create these reservoirs in the hill, and make them into catchment areas. Okay? And then when the water is harnessed, I can generate power, and also my distribution becomes easy, like I told you, because you're distributing it from a height. So, in fact, the Olympic village in Rio de Janeiro was actually powered by this kind of a concept. Hydropower need not necessarily be only about natural things. There could even be artificial interventions which you could possibly think of, and which could lead to this kind of, good gains. Okay, so I hope you can see that you need to look at renewable energy resources as something which you it's not all just there given. You may have to create, okay? And that will require innovation, that will require imagination, that will require policies. It will require a lot of willpower on the part of governments, so that they're not just maintaining status quo. They're doing clever things. Okay, so all of these are the things that can actually boost hydropower. All clear?
Yes, sir.
Okay. Okay. So now let us go on to the next part, which is nuclear power. Okay. Now, what is very interesting is the science which led to nuclear power was actually discovered. It would be a halfway between an invention and a discovery, and it happened around 1938. Okay, now within 5 years, okay, America had already made the atom bombs, okay, and they detonated the bombs in Hiroshima and Nagasaki, okay, around 1944, 1943-44, okay, and the first nuclear power plants to generate power actually came a good 10 years later. In other words, this invention was really looked at for warfare activity to begin with. And the peacetime activity of harnessing it for nuclear energy came almost a decade later. And it was the Russians who in 1954, they set up the first nuclear power plant, 5 megawatts, and later on, the Americans realized the massive value, well, that's not entirely true. They realized the value of it way back even in 1945, because some of the patents were granted to the US around that time on nuclear power plants, but the construction happened in Russia first. Now, but they continued with their war-related, defense-related activities and started focusing, on nuclear submarines, submarines are not like our cars that you can go every second day to the petrol pump and fill up petrol. Okay, I mean, these things sometimes have to be in the sea for months together. Okay, and so where are you going to get so much fuel? Okay, so they realized that nuclear reactors if we can build them in the nuclear submarine, then of course, it will get all its energy, and the first, such nuclear powered reactor, USS Enterprise, you can see 1964, okay, it traveled 26,000 nautical miles, means about 50,000 kilometers, okay. It took 65 days with no refueling. And you can also see that, when you see at it from far, you'll see it's written E is equal to mc squared, because that's what it's based on. Conversion of mass into energy, okay, by Einstein's theory of relativity. That's what nuclear fission is. Okay. Now let us look at typically where we have nuclear power plants. Now this is of course a very old picture, old scenario, 2002. There have been changes, quite a bit of changes, but not dramatic changes yet. Okay, what you find is that the Americans have quite a bit of nuclear power. Okay, when I say quite a bit, they typically would be getting something between 25 and 30%, of their total power from nuclear power plants. It would have been higher, but there were certain terrible accidents, okay, and like the 3 Mile Island, and those things put a halt to the construction of more nuclear power plants. The country which has the largest, number of power plants and the largest percentage of its energy that it gets from nuclear power plants is France. Okay, France derives close to about 72% of its power from nuclear energy. Okay, and part of the reason is because all the original work on nuclear, radioactivity, these were all French. Okay, Marie Curie, okay, Becquerel, they were the fathers, and mothers of what subsequently led to all of this nuclear business. Okay, but Europe had a lot of plants. Okay, and another country which has a fairly large number of plants is Japan, okay? Because Japan did not have any very good source, and you can see in India we have got plants. Okay, they're not very big plants. Okay, but and today typically we get something like 2% of our total power requirement comes from nuclear. So there's a lot of talk about nuclear, but the reality on the ground is very different. Okay? It's just less than 2% is what we get. And at one time around 2009, India had planned to derive something like 28% of its power from nuclear, but it's taking a long time for all of that to happen. So this, whatever I told you, this is really the kind of trends, okay, where, as I told you, I mean, there was a declining trend in the US, in France, it's an increasing trend. On the other hand, Germany, they have decided to phase out nuclear power. The UK is banking on it because they have stopped all their coal power plants. Japan has a large number, and in Asia, we think that it will increase, especially in China and India. With such a large population, okay, and something like 350 gigawatt is what is there, okay, and in India it would be of the order of maybe about 8 gigawatts. So we are a small player relative to the world. Now, let us first, I'm not going to just tell you about that this is this plant, that plant. You know, I'm going to actually take you through the process by which this whole nuclear power came to be. Okay, so that you understand what were the landmark inventions and discoveries that were made. Okay, now because we will we will use these terms frequently, right? Right in the beginning, let me tell you about some processes, and I think many of you would have learnt about these in your high school possibly. Okay, but we will just recap it. There are typically 4 types of decay, you know, which can take place, and these are typically, I'm talking about where you have natural radioactive processes. Okay, like for example, it could be an alpha decay. What it means is that I have removed effectively an alpha particle is a helium. Okay, so the atomic weight goes down by 4. So from 238 it went down to 234, and the atomic number, okay, went down by 2, and so it becomes 23490, and this element is thorium. Okay, so uranium can decay to thorium by releasing an alpha particle. Okay, and these are all releases of particles from the nucleus. Okay, many times their charge, their properties are similar to like an electron, for example, a beta radiation, but it is not released as an electron from the atom. It is actually coming out from the nucleus. Okay, so a beta decay is beta particle is what they found out is it is an electron. Okay, but that electron is coming out from the nucleus. Okay, how does it come out? Basically, what happens is that one neutron, it is as if one neutron lost an electron, okay, and became a proton, because the neutron and proton have a similar mass. Okay, so a neutron is a neutral particle. So if an electron came out from the neutron, you know, it would get converted into a higher positive charge. So atomic number increases from 53 to 54. For example, iodine gets converted into xenon, okay, by emitting a beta particle. Okay, then you have a gamma decay. Gamma decay is a neutral massless particle. It's like a kind of radiation, very, very high energy radiation, but it neither has mass nor charge. Okay, and but when will it come out? Suppose, let's say for whatever reason, just like we form molecules or atoms in excited state, I can also create a nucleus in an excited state. Okay, and then the nucleus can decay. Okay, and that decay, all right, it doesn't change really the properties. It's still thorium. This thorium over here is called thorium, but it went from the excited state of the nucleus to the ground state. Okay, it went to a lower energy state and released a gamma radiation. Then you have a positron. Positron is exactly the opposite of an electron. It has the mass similar to an electron, that means very low mass, okay, but it is positively charged. So when will that happen? Suppose, let's say if I've got a proton, you know, and a positron were released from the proton, then the proton would get converted into a neutron. Okay, and the atomic number would go down by 1. Okay, so like carbon, let's say with an atomic mass of 11 and atomic number of 6, it released a positron, and therefore its atomic number reduced to 5, you know, and the atomic weight remains the same. You know, it's still 11 because this particle has no mass or negligible mass. Okay, so these are typically the kinds of processes, you know, which were known nuclear processes. Okay, now whenever you're looking at nuclear processes, it's always a good idea to look at the periodic table so that you can immediately relate, one to the other. You understand? So if I'm talking about iodine going to xenon, like over here, okay, iodine going to xenon, you can see from the periodic table, that this is iodine, this is xenon, okay. So you can just look at the periodic table and you'll get a good feel for why one element is getting converted into another. Now, what I'll do is I'll take you through how exactly this whole process happened of discovering nuclear fission, okay, and it's a remarkable journey, okay. The interesting thing is that, tell me one thing, who do you think would have invented it? Nuclear fission? What kind of a scientific background would the person have likely had?
Chemistry.
Chemistry. Very good. You have hit upon the right answer, but I'm wondering why. No. Very good.
Because periodic table comes in chemistry.
Oh, because the periodic table. No, that was, well, partly. So yeah, that's a very good point. Okay. Let's just look at it. Okay. He is the man, Otto Hahn, who got the Nobel Prize in 1944. And he got the prize, actually, he got the prize before, but he was put in jail, by the, by the Britishers, because they suspected him of being a Nazi, and so he was awarded the prize 1 year later, and Otto Hahn was actually an analytical chemist, okay, and he and the person who worked with him, Fritz Strassmann, they are the ones who did some remarkably good analytical chemistry work, related to nuclear chemistry, but nonetheless analytical, okay, and and they are the ones who really identified what is going on, okay, and there was this lady who was also a collaborator of theirs, Lise Meitner, who probably made some of the finest contributions in this area. And in 1963, long after this whole thing happened, because this discovery took place in 1938, and in 1963 they interviewed Lise Meitner. Lise Meitner was a Jew, and so she was kicked out of Germany, or rather she fled Germany because she was worried that she will be killed, and fled to Austria, and continued with her work. And Lise Meitner in 1963 said, the discovery of nuclear fission by Otto Hahn and Fritz Strassmann opened up a new era in human history. It seems to me that what makes the science behind this discovery so remarkable is that it was achieved by purely chemical means. Because you would always associate nuclear fission, everything, with it's the domain of physicists. Of course, it later on became the domain of physicists, but not in the beginning. Okay, beginning it was chemists played a massive role, and who was one of those chemists? Marie Curie. Okay, Marie Curie was the one who basically, she and her husband, they isolated two of the most radioactive elements, radium and polonium, from uranium ore, and that is really what got everything going, And Marie Curie is one of those exceptional people who was awarded 2 Nobel Prizes for her work, okay. And the person who really triggered all the work specifically which led to the nuclear fission related things was this man Enrico Fermi, and so these people are not actually the inventors of the process, but they unraveled the process. Okay? The actual doing the experiment, reporting some of the very important results, etc. Those happened with Enrico Fermi. Okay? Now, this person, Otto Frisch, is not very well known. Okay, but he is the person who first coined the term nuclear fission. Today we all use that term, nuclear fission, nuclear fission. Okay? But it was Frisch who termed this. Now, can anyone tell me where possibly the term fission came from? And this class should know. You all should know.
Maybe binary fusion.
Wonderful. Wonderful. I knew one of you will be able to give the answer. Okay. Fission came from biology, because that process, of cell division, etc., and fission was very well known. So it is a term which was borrowed from biologists. Okay. So just keep that in mind. It's just that later on it was called nuclear fission. Okay? But fission as such came from biologists. Okay? Now, this person was the son-in-law of Marie Curie, married Marie Curie's daughter Irene Curie. They're all Nobel laureates. Okay? And he is the person who for the first time discovered artificial radioactivity. What Marie Curie worked on was natural radioactivity. That is, substances which were naturally radioactive. But he was able to induce radioactivity artificially, okay? And in fact, he got the Nobel Prize 10 years before Hahn, in 1934, for his work on artificial radioactivity. And this lady over here was the most daring of them all. She proposed something which was ruled out and discarded by everybody, but she had the guts to propose it, and finally she is the one who turned out to be right. Okay, but she was not recognized by any prize, anything. Okay, she was also a very good analytical chemist, but tragically, she didn't get the credit she deserves. I would actually, in some ways, really look at her as one of the real pioneers of this area. Okay. Now, let us start, try and understand what exactly was the situation, and typically, this is very important that you should know how actually things happen. And everywhere you can see, even in hydropower and this, that, we are talking about 100 some years. We are not talking about eternity. We are not talking of 2,000 years, 5,000 years, 10,000 years. Now, remember the periodic table, right, was as made or drawn by Mendeleev. Okay, was a periodic table which was based on atomic weight. Okay, and it was mostly who in the early 1900s. So you're talking about what, 110 years ago? And he was the one who first remade the periodic table based on atomic number. Okay? And then everything became much more easily understandable. Okay, once atomic number was the concept, and then it led to new kinds of concepts like isotopes and this, that, because they found that there are things with same atomic number, but their atomic weights vary, which Mendeleev didn't know about. Okay, and so mostly was a great man. Okay, now what this periodic table, this is an early periodic table. Okay, but why it is so famous and why it is so important in the context of nuclear energy is that the element at that time which had the highest atomic number was uranium, 92. Other than that, uranium had no real importance. Okay, I mean, it had been invented about or discovered about 100 years before that, but there was no real interest in uranium as such. Okay, but this was to become something which later on became extremely important. Okay, that it was the last element with the highest atomic number, and nothing else was known which had a higher atomic number than uranium. Okay, now comes some remarkable things, which happened. Okay, now what happened was that there was work which was done on the cathode ray tube, and these were very important. Those were the early days of electronics, discovering electrons, all kinds of things that happened. Okay, and around that time, Rontgen had basically shown that cathode ray tubes emit X-rays. Rontgen, by the way, is the first Nobel laureate in physics. Okay, that's his fame. Now, when this man Henry Becquerel, came to know about Rontgen's work on X-ray, okay, what happened was he went in a completely different direction. He found that there are certain natural ores, minerals, which are fluorescent. Okay. Now, what do we associate fluorescence with?
Sir, emitting light.
Right. It is absorbing light and emitting light.
Yeah.
Okay. And so, when he found these things fluorescent, I mean, he thought that must be that because people knew that many things when exposed to light they fluoresce, and so he also thought that these elements, these minerals must be fluorescent because they're absorbing a lot of solar energy. Okay, and so what he did was in the terrace, he would expose these minerals, to very strong light. France gets excellent solar radiation, and so he was, and he thought that just like Rontgen was able to convert an energy source, like an electrical energy source into a very high energy material like X-rays, So Becquerel also thought that maybe, if he keeps illuminating the minerals with light, that solar energy will get converted into X-rays. Okay, and he was interested in seeing if X-rays can be derived, in a method completely different from what Rontgen had found. Okay, but then one day, what happened was that the sky was overcast, there was no sun. Okay, and when Becquerel started looking at these minerals, he said they're still fluorescing, and there's no radiation, there's no sun, so how are they fluorescing? Okay, and then he came up with the concept that no, these things are not going into the excited state because of solar energy falling on them, but these minerals are pre-energized. That is, they're naturally in some kind of an excited state. Okay, and that is what he named as radioactivity. Okay, and all the work was done with uranium minerals. Now these things, they were radioactive, but they were quite weakly radioactive. These raw minerals. Okay. Now Marie Curie and Pierre Curie, her husband, they said, how do we know that there isn't something in this mineral which is actually causing it? It may not be this entire mineral, okay? And they started isolating, they kept on purifying these ores, okay? And, there were some processes where they did something like 5,000 recrystallizations, unbelievable. We cannot even do 2 or 3. I mean, you'd lose your patience, and so from tons and tons of material, they extracted out maybe milligrams of material, okay, and but what they came up with were these two substances, polonium and radium, and polonium was named because Marie Curie was Polish, and so she had come from Poland, so she named it polonium, okay. And later on, after they had isolated this, they found that these substances are more than 1,000,000 times more radioactive than uranium, the original uranium ores. Okay. And now this was a extremely important discovery, okay, because now there was a concentrated source of natural radioactivity, okay, concentrated source. Now, so what happened was that basically after that, Rutherford asked that what's actually going on, with these substances, okay, and effectively found out that the radioactivity happens because of the release of an alpha particle, okay, and which, as we know, is essentially helium, okay, helium minus the electrons, okay, and so radium got converted into radon, okay, 226 went to 222, okay, and 88 protons and 86, so that's really what Rutherford found. And because radium was so radioactive, so Rutherford was able to get a very intense source of alpha particles, which did not exist earlier. Okay. Now, once Rutherford found this very intense source of alpha particles, then of course he made his historic experiment, where he was able to effectively show that if he takes things like a gold foil, or a silver foil, that and he bombards it with alpha particles, that most of the alpha particles go through, but some of it bounces back, okay. And when he found that some of it is bouncing back, what he said is that it must be that an atom effectively has a very dense positive charge, and the rest of it is largely empty space occupied by electrons, and because alpha particles are positive, so most of it is going through that empty space, attracted by the electrons, but occasionally, very, very occasionally, alpha particle goes and hits a neutron, a nucleus, okay, and because of the positive charge, it bounces back, there's backscattering, and therefore he was able to conclude, that an atom is largely a nucleus and surrounded by mostly empty space occupied by electrons, okay. Rutherford also then made the first transmutation, that is converting one element into another, and that was done when he bombarded nitrogen with helium, okay, and it got converted into oxygen, released a hydrogen and energy. Okay? That was a very, very important piece of work. Now, what happened around that time was that there was another very, very interesting observation which was made by some German scientists, okay, that beryllium, when you do similar kind of thing, bombard beryllium with helium, they found carbon, but they could not explain, all the properties of the products that they got, by invoking what was known at that time in radioactivity. Okay, and so this problem was dealt with by Chadwick, a Britisher, and Chadwick said the only way I can make sense of this reaction is if I invoke the emission of a neutral particle which has the same atomic mass as a proton, but it doesn't have the charge of proton. Okay, and that's what he called as neutral, and from that came neutron. Okay, so that was neutron, and so in 1932, the neutron had been discovered. Okay, the 1932 there were many other discoveries. I don't want to go into it, including isotopes. Okay, now when this happened, I showed you Enrico Fermi. Okay, Enrico Fermi was the person who spotted a golden opportunity. Okay, can anyone tell me what it is about the neutron as compared to the alpha particle that excited Enrico Fermi? So Rutherford had found that the nucleus is a dense mass of positive charge. That is the hint I'm giving you.
Sir, can you repeat the question?
Yeah, the question is that, just like Rutherford did this, okay? And here also you can see beryllium, these are light elements, okay? But there was a problem when they extended the study to high atomic weight elements, okay? And what was the problem? What could have been the problem in bombarding such high atomic number elements with an alpha particle?
They repel each other.
Wonderful. Wonderful. Okay. And because when you have a high atomic number, there are so many of these protons which are packed together in a tiny space, so the repulsion is enormous. Okay. So an alpha particle can never come close to approaching a nucleus. Okay. And of course, later on, they could do it when they generated or developed new kinds of generators, etc. But in earlier days, it was not possible because the uranium, the alpha particle would get repelled, and it was Fermi who said, oh, a neutron has the atomic mass of a proton, and so it is 1/4 of helium, so it is quite heavy. Okay, what do I need if I want to smash against something? Like if I've got a car, I'm driving it and it goes and smashes. What is it that causes destruction or accidents? Is momentum, right? What is momentum? Mass into velocity. I can have a beta particle. Beta particles also come out with enormous velocity. Gamma particles also come out with enormous velocity, but they don't have mass, negligible mass. Okay, but not a neutron. Neutron is heavy, and yet it is, when it's coming out, from the nucleus, it is coming out at tremendous speed. So I get tremendous momentum. Okay, and because it is neutral, it doesn't have any difficulty penetrating the nucleus. Okay, so Fermi was the one who recognized that, and then Fermi started bombarding heavier elements with neutron and wanted to see what is formed. Okay, that is what happened. Okay? And in the meantime, I told you about Joliot-Curie. Joliot-Curie got the Nobel Prize because he was able to artificially create elements in the excited state and made them radioactive. Okay, and these ones could then emit different kinds of radiation and get converted from one element to another. Okay, and this was very important. But up till that point, all the work was done with alpha particles, but it was Fermi who then started using the neutron, and started bombarding heavy elements, with neutron, and was able to finally, create this kind of artificial radioactivity of heavier elements induced by the neutron. Okay, is that clear to everyone?
Yes, sir.
Clear? Huh? And then, of course, it emits beta particles or positron, various kinds of things. In the case of Fermi, when he bombarded the iodine with a neutron, what happened was a beta particle came out. Beta particle means the atomic number will, what will happen to the atomic number? It will go up, right? So 53 became 54. Okay, so that's very interesting. So there was an increase in the atomic number from 53 to 54. So iodine first was bombarded with a neutron, it went into an excited state, and then this excited material, released a beta particle, and it got converted into atomic number 54. Okay, and basically with the loss of a beta particle, which is the electron. So what Fermi did, one was he was able to bombard heavy elements, he was able to bombard them with neutrons, and Fermi detected from artificially excited elements, the release of beta particles, whereas earlier, what they had found was the release of positrons, typically when they did work with helium, with alpha particles. So there were important differences. Now, tell me one thing. Fermi went to the periodic table, okay, and Fermi now had a great problem in his hands. What is that problem? Which he wanted to work on.
Stabilize the reaction from one particle to another.
Stabilize the reaction. Which reaction?
That neutron bombardment or alpha particle.
Right. And then what, by stabilize, what do you mean?
In the forward direction.
No, means it will get converted into something else, right?
Yes, sir.
That's what you mean?
Yes, sir.
Huh? Now, very nice, beautiful answer. Now, take it to the next logical thing, now that you have said it so wonderfully. Relate this, okay? Relate this, okay? And now see the periodic table. And so, which is the experiment that attracted him a lot? You are almost there. You have basically given the answer. But I want your answer to be more crisp. Well, what did I tell you? That uranium was the highest atomic number, right? No element was known beyond atomic number 92. Correct?
Yes.
So, Fermi said, if I bombard uranium with neutron, and if it emits a beta radiation, then I would have created an element with a still higher atomic number. In other words, I would have created a new element which was not known. All these other elements were known. You understood?
Yes, sir.
Okay. And so what happened was Fermi went ahead and did that experiment. Okay. And Fermi also found that he was getting beta radiation coming out. Okay. And then Fermi concluded that he has made a new element, element 93. You understood? Okay, and published the, I think it was, I think in those days, later on he published it in Nature, but there were articles which came out in newspapers, etc., talking about that Fermi had created a new element. Okay, and what happened was, the moment it happened, then all the other people started asking that, can we figure out whether what Fermi is saying is correct? Okay, and now then what happened was that Marie Curie's daughter, Irene Curie, and another person, they basically repeated Fermi's work, and they found that it's releasing a beta particle. Okay, but what happened was that if because they knew their chemistry, so but what she said is that, it's funny, this whatever I'm getting is not this element 93, but I'm getting something which looks like lanthanum. Okay, now let us try and understand what is lanthanum. Okay, now what is lanthanum? This is barium. Okay, after that you have the lanthanide series. So from here is lanthanum. Okay, and this is the actinide series. This is, this is that actinide series. Now this is uranium. Okay, over here, and this is what they were bombarding with neutron. Okay, now what happened was, they said, I mean, what will happen? How can it form lanthanum? Because to form lanthanum, I would have to skip so many elements. And what they had typically found was, that whenever there is a radioactive decay, elements are formed typically one to the right, two to the right, two to the left, one to the left, that kind of thing. Okay, by emitting a alpha particle, positron, beta particle, but nothing where I can jump, one entire period, one entire row, and I find lanthanum. And she said, but then everybody started ridiculing Irene Curie, and Irene Curie got so scared, with everybody. It was something like Darwin got scared of Lord Kelvin, Irene Curie got scared, and Irene Curie said, no, it looks like I made a mistake. I think it was not lanthanum. I think it was more like actinium. Okay, which means, she just said, she just said that it looks more like this, when in reality she was quite convinced that it is actually this. All right. So then what happened was, at that time, I told you that there was another great person, Ida Nodak. Nodak said, maybe Irene Curie was right, and asked Fermi, on what basis have you said that you have created a new element, element 93? How do you know? Have you looked at all the elements of the periodic table? Did you look and did you rule them all out before proposing a new element? Fermi said no. They said, so how can you say that you made a new element? Common sense says that you should first look at all the elements that already exist, make sure that it is none of those, then only you can say. Okay, and what then Ida Nodak said, is something which was considered revolutionary. Okay, and Ida Nodak said, how do you know that an element, the nucleus cannot just break up like a papad into two, okay? And so this is Ida Noddack saying, when heavy nuclei are bombarded by neutrons, it is conceivable that the nucleus breaks up into several large fragments, which would of course be isotopes of known elements, but would not be neighbors of the irradiated elements. Okay, in other words, because that's what was known, they were always neighbors, But when Irene Curie had found lanthanum, although she backed out later on, Ida Noddack said maybe it fragments, into bigger size chunks. They don't just push a little bit here and there. Okay, but everyone laughed at Ida Noddack, said no such thing has ever been found, so forget about it. And they forgot about it. Okay, but later on, I mentioned to you about Lise Meitner. She did a calculation, and from that calculation, she came to the idea, that indeed this kind of fragmentations are possible. Okay, and what she also calculated, that when a nucleus, like let's say fragments like that into two, that it releases something like 200 million electron volts of energy. Okay, and now she did not exactly apply E is equal to mc squared. She derived this number in a different way and published a very short paper, not even one page, half a page, I think, in Nature, giving her explanations. Now, let us try and quickly see that 200 million electron volts, okay, what it means, okay, and suppose, like, let's say, and this is per nucleus, one nucleus, fragmenting into two, okay. Now, suppose I say that I want to generate 1 kilowatt of power, okay, then how many such fragmentations do I need to have in a second? Because kilowatt means joules per second, okay. Now, 1 electron volt is equal to 1.6 into 10 to the power minus 19 joule. So 200 million electron volts is equal to 200 into 10 to the power 6 into 1.6 into 10 to the power minus 19 joules, 3.2 into 10 to the power minus 11 joules. That's what it comes to. Okay, now what is a kilowatt? Kilowatt is 10 to the power 3 joules per second. So I basically have to take 10 to the power 3, divide that by 3.2 into 10 to the power minus 11, and roughly then we are talking about 3.125 into 10 to the power 13 fissions. That means to generate 1 kilowatt of power, I need 10 to the power minus 10 Avogadro number. And so when people realize this, they then realize what an enormous source of energy, nuclear energy can be. Okay, and that was really came from the work of Lise Meitner. Is that all clear to you? Did you understand the calculation? Everybody understood?
Yes, sir.
Yes, sir.
Okay. Okay. Then something very interesting happened. It was at that time that Otto Hahn, started doing a much more detailed analytical work. Okay, and I will send you his Nobel lecture. For those of you who are interested in such things, you can read the Nobel lecture, see if you can understand it. Okay, it's written very beautifully. Okay, and basically what Hahn was concluded was that he was able to, through a very, very deep and intense study, he and Strassman were able to identify the formation of barium and krypton. Okay. In other words, what happens is that these two, uranium has an atomic number of 92. They fragment into this, it becomes 56 and 36, 92. Okay. But the problem is that the atomic mass of uranium is U-238, uranium-238. Okay. Now, if you break this up, then they said, okay, let us find out which are the isotopes of krypton and barium which are known, and they found out, that they could never add up, to the atomic weight of 238. Even if they took the highest natural isotope atomic weight that is known, they could never add it up, and they always got a gap, and so what then happened was that this person Otto Frisch, whom I mentioned to you about, he realized, that this fission process is induced by a neutron, okay, but the fission process is creating more neutrons because these isotopes do not add up to 238 or and so they had to basically invoke that some neutrons must be getting lost in this fission process. In other words, if I'm bombarding with one neutron, I'm ending up with 3 neutrons. Okay, and they did not understand the significance of it, Otto Hahn and others. Okay, but it was Frisch who realized that, oh, what that means is that I bombard with 1 neutron, I get 3 neutrons coming out. Now 3 neutrons can go and bombard 3 uranium, and from 3 uranium again I will generate 9 uranium neutrons, and therefore it will set up a chain reaction. Is that clear?
Yes, sir.
And
Yes,
that was actually, sorry, it was not Frisch, but a person by the name of Fluge. Frisch gave the name nuclear fission, but it was Fluge who actually proposed this. And this is what Otto Hahn says in his lecture. If more than 1 fresh neutron is produced and the process is so arranged that all the fresh neutrons strike uranium atoms, then we have a chain of continuously renewing fission reactions which, like an avalanche started by a snowball, can attain enormous dimensions. Okay, and so was created, the concept of a chain reaction. Is that clear to everybody? Understood how the concept of chain reaction came? Because they analyzed the isotopes. When they added up the heaviest isotopes, even then they could not match the atomic weight of uranium, and they said, therefore, it must be, that neutrons are getting released, in this whole process.